Hey guys, my name is IBM and today I'm solving waves and superposition. This is going to be lesson, I think it's going to be lesson 8. And lesson 8 will be, I think it will be introduction to superposition. Remember I said I called the topic waves and superposition, but these are two topics in one. So um, we may study them differently, but I've tried my level best to just teach it as a single topic. That's why it is a continuation of waves and superposition. Just remind you of the course outline. Remember the topics you are supposed to cover in AS Physics, and those which I recorded, which are in red, have already been recorded, and each of them has a playlist. And we are currently dealing with waves and superposition. These are two topics. So far, we have finished the first part, which is waves. So unit 7.0 is supposed to be waves and unit 8.0 is supposed to be superposition, but I just called it waves and superposition. So let's talk about superposition. And in superposition, we shall study four important areas where we shall talk about standing waves, standing or stationary waves. We shall talk about diffraction of waves. We shall talk about interference, and then we shall talk about the diffraction grating. When those four areas are covered, then we shall be completely done with the waves and superposition. So without wasting time, let's go to the first part, which is going to be standing or stationary waves. So standing or stationary waves. Now, most of the questions in our waves and superposition come from this part of stationary and standing waves. Therefore, you need to pay a lot of attention, and you should follow the concepts here because they are not really much related to what you covered in IGCSE. So most of the concepts here are going to be relatively new to most of us, but of course they just build on what you covered in IGCSE. They just like advancing in waves. I want you to recall or to note that the waves that we hear from a string musical instrument such as a guitar are created by vibration of its strings. To produce waves on a guitar string, you have to pluck the string. So the notes that we hear from a string musical instrument are created by the vibrations of its string. And the wave patterns on the vibrating strings are called stationary waves. Of course, when you pluck a string, the string itself vibrates, say, up and down, producing transverse progressive waves. But of course, a progressive wave propagates from one end to another and undergoes reflection. So a continuous incident wave and a reflected wave from the other end are going to be meeting to produce what we shall be calling stationary waves or standing waves. So these waves, the waves in the air which carry the sound to our ears transfer energy and are therefore called progressive waves. In the previous lessons, we mentioned that a progressive wave energy is transferred from one point to another, and there was no transfer of matter, but energy was propagating. And we said waves which transfer energy from one point to another are called progressive waves. However, it is from these progressive waves which transfer energy from one point to another that can produce stationary waves. And again, these stationary waves can again produce progressive waves in the surrounding medium of air. For example, when you pluck a guitar string, you create a progressive wave on one point, which propagates through the string to the other end. Then another progressive wave is reflected from the other fixed end back in the opposite direction. These two produce a stationary wave around the guitar string. But again, this stationary wave causes the surrounding air molecules to vibrate, creating a progressive wave which travels as a longitudinal wave or a sound wave towards our ears. So the waves in the air which carry the sound to our ears actually transfer energy and are therefore called progressive waves. So from a progressive wave, we can produce a stationary wave, and a stationary wave can also produce a progressive wave in air in form of sound, which can propagate to our ears. That's how sound wave from a guitar string reaches our ears. So what do we mean by stationary wave? So to distinguish this from a progressive wave, a stationary wave or stationary waves are those waves which do not transfer energy. There is no transfer of energy for these waves. So they do not transfer energy and consist of nodes and antinodes. For a progressive wave, we're talking about the crests and the troughs in most cases. For a stationary wave, we shall be talking about nodes and antinodes. What are these nodes and antinodes? We are yet to see what the nodes and antinodes are. So generally, such waves are formed by superposition of a forward wave and a reflected wave. So I said when you pluck a guitar string, a progressive wave travels from one point to the other fixed end. Then there is another wave which is reflected from the fixed end in the opposite direction. So when these two waves meet, we have what we call superposition. That's why the unit is called superposition of waves. So both longitudinal and transverse types of waves can form as stationary waves. So whether the wave is longitudinal or it is transverse, both of them can still produce or can still form stationary waves. So we can have stationary waves in the pipes, in acoustic instruments where wind or air has to be blown into the pipe to produce the sound. We can also have stationary waves formed on a string. So both longitudinal and transverse types of waves can produce stationary waves. So all waves produce stationary waves. So to demonstrate how stationary waves are formed, let's consider the following slide or the following animation. So when a reflection occurs at a free end, there is no reversal of phase. However, what arrives as a crest returns as a crest and a trough as a trough. So what is happening? So we are producing what we are calling a stationary wave. A wave which is propagating from left to the right is traveling or is transferring energy to the right hand side. And what happens is that when the incident wave continuously propagates from left to right, the reflected wave is going to continuously propagate from right to left. So the process continues, and if these two meet at a point, then they undergo what we shall be calling superposition, and they will result into what we call a stationary wave, which can be demonstrated here. So we have the incident wave, which is leaving, let's say, the left hand side to the right hand side, and it is in blue. And we have the reflected wave, which is going to be leaving the right hand side to the left hand side. And we have what is formed. And what is formed is what is going to be called the stationary wave. Now, I want you to notice that there are certain points which are always permanently at zero amplitude. For example, let me pick a pen. When you look at the incident is a progressive wave. The reflected is also a progressive wave. But when you look at you notice that for the incident and the progressive, it's like the crests are moving. The incident and the reflected, it's like the crests are moving. For the incident, the crests are moving in that direction. For the reflected, the crests are moving in the other direction. But I want you to look at the resultant wave. For the resultant wave, it's like the crests. It's like we don't have our crests moving from one end to another, but we have points. For example, this point here and this point here, this point here, this point here. Where, if you are very careful, you notice that at these points, when a stationary wave is formed, at these points, it's like they are always permanently at along the horizontal line, which is going to be called the equilibrium position. Yet there are these points here where the particles are always vibrating with the maximum amplitude here. So there is this point here where particles are always vibrating with the maximum amplitude, and there is this point here where the resultant is always at this point here, even when these two waves are combining, when they are meeting. So these two points where the wave is always, the resultant wave is always, the particles are always permanently at rest when the two waves combine or meet at a point. These ones are the ones we are going to call nodes, positions for the nodes. A region where particles are going to be permanently at rest, where particles are going to have zero displacement. Then we have here where particles are now always vibrating with the maximum amplitude, and these ones are going to be called regions of the antinodes. So we have the antinodes here. So for a stationary wave, we have the nodes and antinodes, and the nodes and antinodes do not move through the wave. They are always at the same constant points. Unlike the progressive waves that we have seen, where the incident wave has its crest propagate and the reflected wave has its crest propagate, for the stage, when a stationary wave is formed, when these two waves superpose, or when these two waves meet, the nodes and antinodes do not move through the wave. They remain in their fixed positions. So that is what we mean by a stationary wave. Okay, so we are still demonstrating stationary wave. So the waves, or to understand the concept of stationary waves, let us consider a slinker spring, because a slinker spring is easily found in the laboratory. So you might have seen such a coil of spring where you can cause it to move up and down, for example, to cause a wave to propagate from one end to the other end. So a wave is sent which makes the crest to move from the left hand side to the right hand side. So in other words, the energies are propagating from left to right. And if at the fixed end, what arrived as a crest is going to return, and it is going to move in the opposite direction. But remember, a continuous pulse, or a continuous a continuous progressive wave is being sent from the left towards the right. And then we now have a reflected wave which is now leaving the fixed end from the right to the left. These two waves are going to continuously be meeting, and as they meet, they result into what we call superposition. And if they superpose, they form what we are going to call a stationary wave. So it's like to superpose is like to combine, to meet, or to come together and give a resultant, which resultant we are yet to establish. So a progressive wave, which in this case is transverse, is propagating from left to right, and the reflected wave pulse, which is also transverse, is now leaving the right hand side to the left hand side. So these two are going to be meeting at a point. So when a progressive wave pulse traveling along a slinky is reflected when it reaches the fixed end, and then the reflected pulse has the same amplitude and it has the same frequency, because it is just the same wave which has just been reversed. So it is going to have the same amplitude and the same frequency. So if it has the same amplitude and same frequency, it means when a crest meets with a trough, a crest of the incident meets with the trough of the incident, these ones are going to completely cancel out because the amplitude is the same. We can say amplitude upwards is positive, amplitude downwards is negative. So when you sum up, if they have the same magnitude, total amplitude would be zero. That's where we are going to have the nodes. But if a crest is aligned with a crest, it means the amplitude is adding up. If a trough is aligned with a trough, it also means the amplitude is adding up in that case. So that means we are going to get a resultant which is going to be probably bigger. So they have the same amplitude and the same frequency as the incident pulse. So what happens is that the reflected pulse will pass through the incident pulse. In other words, they will combine, or they will meet to create a new pulse, which is going to be called a resultant. So we say interference will take place between the incident and the reflected pulse. So when the incident and reflected pulse meet at a point, interference is going to take place, because the reflected pulse is going to tend to pass through the incident pulse. The effect is going to be superposition in that case, and this effect is going to lead to points where particles are permanently at rest, or where there is completely no vibration, and points where particles are vibrating with the maximum or with the highest amplitude. In other words, particles vibrate to maximum or to the highest, to a bigger displacement, which we are going to call the amplitude. So that is what we mean by creating a stationary wave. So the waves interfere, producing a wave pattern below, in which the crests and trough do not move. So if we just consider one situation for the fundamental mode, where this was maybe the incident and we have the reflected, but they have met at a point, this results into a point here where particles cannot be moving, and of course a point on the other end where particles are not moving, and somewhere in between where particles may vibrate with the maximum amplitude. So we say a stationary wave is created when two waves traveling in opposite directions interfere. So the incident was moving to one direction and the reflected was moving in the opposite direction. They had the same amplitude, same frequency, and they met at a point. So they have undergone what we call interference, resulting into what we are calling a stationary wave. So as the waves pass over each other, constructive and destructive interference occurs. So we shall talk about the types of interference later on, but these are the types of interference. We have constructive and destructive. Of course, their English meaning relate to what they really mean in physics. For example, we are going to see that when constructive interference occurs, a crest has met with a crest. A crest of the incident wave has met with a crest of the reflected wave. So what happens when a crest adds to a crest? The resultant is going to be a bigger crest. Then destructive interference is going to happen when a crest meets with a trough. So when a crest adds to a trough, we have what we call destruction. There is cancellation since they have the same amplitude. So resulting in positions of maximum particle displacement, which we are going to call the antinodes. Maximum particle displacement, which we are going to call the antinodes. And then we have a zero displacement, which we are going to call the nodes. So here at the antinodes, particles are vibrating with the maximum amplitude. And at the nodes, particles are going to be vibrating with the zero amplitude. So in a nutshell, we are saying stationary waves are formed in a medium when you must have at least two waves. These two waves must be having equal amplitude and of course equal frequency. They must be traveling with the same speed, but they should be in the opposite directions along the same line, and they must meet at a point. So you will be asked to describe how stationary waves are formed. So you must have an incident wave and a reflected wave. Because the incident and reflected wave have the same type, they will have the same amplitude, they will have the same frequency, and they will move with the same speed, only that they will be moving in opposite directions along the same line. And when they meet, they form what we call a stationary wave or a standing wave. So stationary waves are formed in a medium when two waves of equal amplitude, frequency, but traveling with the same speed in opposite directions along the same line meet at a point, or they superpose at a point. This forms what we call a stationary wave, or that is how stationary waves are formed. To fully understand a stationary wave, we must introduce the concept of resonance. We shall explore in more details resonance in paper 4 in a unit called simple harmonic motion and oscillations. But we should use the concept of resonance here briefly. So if a string fixed at one end is displaced up and down, it forms what we call a stationary wave pattern. When one end is displaced, a progressive wave travels from the free displaced end towards the fixed end, as we have seen, and when it is reflected towards the fixed end where it is reflected back towards the source. So we have a progressive wave towards one end and it is reflected back towards the source. And when the incident and the reflected wave superpose or they meet at a point, they form a stationary wave. So the incident and the reflected wave superpose to form a stationary wave. In a similar way, If a string is plucked and allowed to vibrate freely, there are certain frequencies at which it will vibrate. So when you pluck a guitar string, depending on the length of the guitar string, there are certain frequencies to which a guitar string is going to vibrate. The amplitude of vibrations of these frequencies is large. This is known as resonance. So when you pluck a guitar string, there are certain frequencies at which the string vibrates. And at those frequencies, the string vibrates with a large amplitude. And this is what we call resonance. So at the points where the amplitude is large, then we have what we call resonance. And we shall explore resonance in more details when we reach our A-level paper 4. But at least we know that when we get a maximum amplitude, then we have resonance. Remember, amplitude is also related to loudness. The higher the amplitude, the louder the sound, if it is sound. So if we can hear maximum sound or maximum loudness, then we have reached a resonance point. So there are certain frequencies at which a material or a guitar string vibrates with maximum amplitude, and those frequencies are later on going to be called resonant frequencies, maybe in A-level paper 4. So let's explore now these resonant frequencies using the modes of vibration of a stretched string. So our strings vibrate according to how they are plucked. A guitar string is going to vibrate according to how you pluck it. And the different ways in which the strings vibrate are going to be called harmonics. You may not always need to understand the meaning of the word harmonics for AS level physics, but the different modes of vibration or the different ways in which a string vibrates when it is plucked is going to be called harmonics. We have the simplest way a string vibrates. We are going to call the fundamental mode of vibration, fundamental, basic, and we shall always call the first harmonic. The word harmonic in this case is referring to the different ways in which the string is going to vibrate or the material is going to vibrate when plucked. And we have the first harmonic, which is the fundamental, and this is the simplest. The simplest way in which a stretched string can vibrate, and we are going to see this later on. So this is what we call the fundamental mode of vibration of a material, the simplest mode, the simplest way in which the material can vibrate. That is the fundamental mode, or we can call it the first harmonic. But like I said, the word first harmonic may not, the word harmonic may not be used many times in AS physics. So this is called a fundamental mode of vibration or the first harmonic. At the ends of the first harmonic, at the ends of the string, there are no vibrations. At the ends of the string, if you had a guitar string, at the ends of the string there are no vibrations, so we expect the particles at the ends to be permanently at rest, and those points are going to be called nodes. Then at the middle or at the center, we have a point where the amplitude is maximum, and we are going to call those points antinodes. So this is what I was talking about here. Here we have a guitar string which is being plucked. The simplest mode of vibration of this guitar string is when it just forms a single loop during its vibration. So there are points on the other fixed ends where the particles cannot vibrate or where the string is not vibrating, and those points we call them nodes. So regions or points where particles are permanently at rest are going to be called nodes. Then there's a point at the center, somewhere in between the nodes, where the particles vibrate with the highest or the maximum amplitude. So between the center, between the two nodes, there's a point where particles are vibrating with maximum amplitude, and this is what we call the antinode. I want you to note that unlike a progressive wave, for a stationary wave, the nodes and the antinodes do not move along the string. They remain at the same positions throughout. Yet for a progressive wave, we saw that the crests and the troughs were propagating through the material. But for a stationary wave, the nodes and antinodes remain in the same positions. So the simplest mode of vibration we have seen is called the fundamental mode. Therefore, its frequency is going to be called the fundamental frequency. So the lowest frequency, the lowest audible frequency is called the fundamental frequency. And this one corresponds to one antinode as we have seen the previous diagram, or I can even bring it here. So the simplest mode of vibration is the fundamental mode, and the frequency of vibration is going to be called the fundamental frequency. So if the length of the string was L, and in the fundamental mode of vibration, L formed half a cycle. You notice that this is half of a cycle. This mode of vibration is half a loop. I mean half of a complete cycle, because for a complete cycle, if it is a complete cycle, we are supposed to have that part and this part here for one complete cycle. But if we have only this part here, then this is only half a cycle. This would be the other part, the other half. So this is the fundamental mode of vibration. So it means the length L is giving us half of a cycle. Because the length can be rated to distance, so this is going to be half of a wavelength, which therefore implies that the wavelength lambda is supposed to be twice of the length of the string in the fundamental mode. But of course, if we use the general wave equation, which states that V equals to lambda times F, if I try to make F the subject, F is going to be the speed of the wave divided by the wavelength. So F is going to be V divided by 2L. So this is going to be the frequency of the wave on the string in its fundamental mode, which we shall always label as F naught. So if V is the speed of the progressive waves which have interfered to produce the stationary wave, then from L equals to a half of a cycle or half of wavelength, then it means lambda is going to be equal to 2L. And from the general wave equation, V equals to lambda F. So we make F the subject and substitute. F naught is going to be equal to V over 2L. So we say the frequency of the fundamental mode, which is the first harmonic, or the frequency of the first harmonic, is going to be V over 2L. So when I write F1, it is meaning, the one here is meaning first harmonic, because the fundamental mode is the first harmonic. So the frequency of the first harmonic is going to be equal to the same as F naught, which is going to be V over 2L. You should be able to establish such a relationship because it helps you to do a lot of calculations. Let's see what happens if we increase the frequency beyond the fundamental frequency, or we change the mode of vibration so that we have more vibration. So we shall talk about the second harmonic, which is later on going to be called the first overtone. You may also not mention the term overtone many times in this curriculum of AS. But of course, overtone is just a frequency higher than the fundamental. So we can have first overtone, second overtone, and so on and so forth. So the second mode of vibration after the fundamental has now two loops and is called the second harmonic. So we are calling it second harmonic because it's going to have two loops. Sometimes it's going to be called the first overtone. But I said an overtone just means notes of higher frequency. Frequency higher than fundamental note or fundamental mode are the ones which constitute overtones. Each of us has different overtones, and these different overtones can help us distinguish our voices. People with so many overtones have the best voices and can sing better than people with a few overtones. So overtones are notes of frequency higher than the fundamental mode or higher than the fundamental frequency. So the length L of the string at second harmonic corresponds to one complete wavelength. So if we look at this diagram here, we now plucked the string so that in the same length L, instead of having only half a cycle, we now have two cycles in the same length. So remember, the length of one cycle is the wavelength, so it means the length of the string has given us two cycles. Has given us a full cycle. So it means if I use the general wave equation, frequency is equal to V over wavelength, it means the frequency F is going to be V divided by, it remains V over L. But remember the first one, we saw that F1, which was the same as F0, was V over 2L. So how is this equation here related to this one here? It means I have to multiply the first frequency by 2. So this one is the same as twice F0. So this is going to be called F2. So the second mode of vibration gives us a frequency which I'm calling F2, and F2 is twice F0. So if we let F2 to be the frequency of the second harmonic, and then from the equation V equals lambda F, we have got F2 is equal to V over L, because there is one complete cycle in the length L, so the length L is equal to the wavelength. And when I multiply this by 2, notice that F2 is going to be the first equation, which was F0, which was V over 2L that we got previously for the fundamental mode, and F2 is going to be twice into V over 2L. And when we simplify this, F2 is going to be equal to twice F0, or F2 is going to be equal to twice F1. In other words, the frequency of the second harmonic is twice the frequency of the first harmonic, or the frequency of the second harmonic is twice the fundamental frequency. Suppose we increase this even further, maybe to the third harmonic. So to the third harmonic, of course, here we expect to have 3 loops. So the third harmonic, or the third mode of vibration, is a pattern with 3 loops. This has been illustrated in this animation, which I don't know whether it is visible to us, where we have 3 loops. Now this is just a string that you see in the animation. But of course, in darkness with an illumination, it appears as if we have a 3-dimensional object here. So we have 3 loops in this case. In the same length L, we have 3 loops. So this is a half a cycle, another half a cycle, and another half a cycle. So it means the length L is giving us 3 halves. Sorry, 3 halves here, I think it is 3 over 2. So the length L is giving us 3 halves, which is 3 over 2 of a cycle, or it is giving us 1.5 cycles. 1.5 cycles is 3 over 2 of a cycle. So it means if I use the equation frequency is equal to speed over wavelength, the wavelength here, when I make lambda the subject, lambda is going to be twice L divided by 3. So this becomes V divided by twice L over 3, which becomes 3V divided by 2L. So the frequency here is 3V divided by 2L. And remember, we got F0. The fundamental mode was V divided by 2L. So it's like we have multiplied the fundamental mode by 3. So this is the same as 3 times F0. So in that case, the frequency here is 3 times F0 for the third harmonic. Now the third harmonic is called the second overtone. The first overtone, remember, overtone is the frequency above fundamental. The first frequency above fundamental is the first overtone. The second frequency above fundamental is the second overtone. But the first overtone was the second harmonic, and the second overtone is the third harmonic. The third overtone would be the fourth harmonic, and so on and so forth. But like I said, you may not always use the terms harmonic and overtone in this curriculum. So we have let F3 be the frequency of the third harmonic, and we have seen that L equals to 3 over 2 lambda, which implies that lambda is 2L over 3. And from the equation V equals to lambda times F, we got that F3 would be equal to 3V over 2L. So this implies that F3 is 3 times V over 2L. And V over 2L, remember, was F0. So it means F3 is going to be equal to either 3 times F0, or it is going to be 3 times F1, where F1 was the first frequency of the first harmonic, which is the same as the fundamental frequency. So what is the pattern here? If you recall, if you have been following, we have seen F1. We have seen that F1 was equal to F naught. We have seen that F2 was equal to twice F naught. And now we are seeing that F3 is equal to 3 times F naught. So any mathematician will be able to see that Fn is going to be N F naught. So in general, the frequency Fn of the nth mode is a whole number multiple of the fundamental frequency. So in general, Fn is going to be equal to N times F naught, where N is equal to 1, 2, 3, and so on and so forth. And then also, look at the lengths. In the first one, we saw that L, I think in the first one, we saw that L was equal to a half of wavelength. Then we saw the second one, L was equal to wavelength. The third one, we have seen that L is equal to 3/2 of wavelength. So this was L1, L2, L3. So what is L4 going to be? So L4 or Ln is going to be equal to, so for the nth harmonic, the length is going to be related to, what is the relationship here? So this is going to be N. If I get N times a half of lambda, I'll always get, for example, for the first one, if N equals to 1, I get a half L. If N equals to 2, I get if N equals to 2, I get L2 being equal to lambda. If N equals to 3, I'll get L3 to be 3 lambda over 2, and so on and so forth. So the length is going to be given by the equation L equals to N into a half times lambda, where N is going to be any number from 1, 2, 3, 4, and so on and so forth. So that is the general expression for the for the modes of vibration on a string. All along we have been considering a string. Later on, of course, we shall consider pipes. But for now, we have been concentrating on a string. So we know the equation relating the frequencies to the fundamental. We know the equation relating the length to the wavelength, and so on and so forth. Points to note. A few things we need to note here. Number one, the point where the particles are permanently at rest is known as, or are known as, the nodes. Points where, or regions where particles are permanently at rest, we have called that the nodes. And of course, these points result from what we call destructive superposition or destructive interference, whereas where waves always meet in what we call they're always out of phase by pi radians. And in one of the units, I think when we're talking in one of the lessons, I think it might have been lesson 2 or 3, pi radians or 180 degrees out of phase is what we call antiphase. So waves are meeting with a crest aligning with a trough. They form what we call destructive interference. The crest cancels out a trough so that the resultant amplitude is going to be horizontal line, or it is going to be zero. The resultant is going to be zero. So such points where particles are permanently at rest are going to be called the nodes. If I take you back to the fundamental mode of vibration, where we had a fixed point here and a fixed point there, and I will just complete the loop on the other side. We say that we have a node here, and a node here, and an antinode here. So these points are considered to be formed when waves are 180 degrees out of phase. The particles could be in the same point, in the same position of their vibration, or they have reached the same stage, but they're vibrating in opposite directions. So that is 180 degrees out of phase. That's what we called antiphase. Then the midpoint, or the points midway between successive nodes, will have their particles vibrating with a maximum amplitude. And these points, we have already called them are the antinodes. So the points where particles vibrate with maximum amplitude, not displacement, because displacement, amplitude is a maximum displacement. By this time, unlike a progressive wave where all particles were reaching the same amplitude, for a progressive wave, different particles have different amplitudes. Different particles have different maximum displacements. Therefore, there are those particles which have maximum displacement bigger than others. So those ones with the highest maximum displacement is what we call are the ones which are at regions or at points where the points we term as antinodes. So points where particles vibrate with the maximum amplitude in a stationary wave are the ones we are going to call the antinodes. So these result from a constructive superposition or constructive interference, which we shall explore in more details. These ones is when waves meet in phase. For example, a crest meets with another crest. They align up. Or a trough meets with another trough. Remember, these two waves are supposed to be moving in opposite directions. A trough of a wave moving to the right meets with a trough of a wave moving to the left. This results into constructive superposition or constructive interference, which we shall talk about in more details later on or in another lesson. So I want you to notice that the distance between a node and a node, we have already seen that this length here, this is half a cycle. So the distance between a node and a node is considered to be half of a wavelength. So the distance between two adjacent nodes is always going to be half wavelength, which also means if there was an antinode here, it means the distance between a node and an antinode is a quarter wavelength. Therefore, the distance between an antinode and another antinode which could be there should also be half wavelength. So the distance between two adjacent means one to the next, is also going to be half wavelength. And therefore, the distance between a node and a neighboring antinode is a quarter of a wavelength. Because between two nodes there is an antinode, so it means the distance between a node and the next antinode and the neighboring antinode is going to be a quarter of a wavelength. These quantities here are very important in calculations. Okay, so what are therefore the general characteristics of a stationary wave? Let's explore now or sum up the general characteristics of a stationary wave. In comparison to a progressive wave, we know that a stationary wave does not transfer energy. So for a stationary wave, no energy is transferred. But of course, we saw for a progressive wave, energy was transferred. Of course, you recall that as the stationary waves are produced due to superposition of two identical waves, the incident and the reflected, traveling with the same speed in opposite directions. Therefore, at any point of the medium, the amount of energy flowing in one direction, say to the left, is the same as the amount of energy flowing in the opposite direction, say to the right. So the amount of energy flowing to the right is the same as the amount of energy flowing to the left. So there is no net flow of energy in any particular direction. Therefore, there is no net transfer. There is no net transfer of energy in a stationary wave. No net transfer of energy in a stationary wave. So consequently, in a stationary wave, there is no net flow of energy in a medium by means of a stationary wave, but the particles of the medium vibrate, forming peaks along their motion. The particles themselves vibrate. That's why we have the nodes and the antinodes. That's number one. There is no net transfer of energy in a stationary wave. Number two, we have seen nodes and antinodes. So it has nodes and antinodes. With with nodes, particles being permanently at rest, whereas the antinodes, particles vibrate with the maximum amplitude. Remember, these nodes and antinodes occur alternately at equal distances. They always occur at equal distances along the wave. So the amplitude of vibration, therefore, is not constant. The amplitude of vibration increases gradually from 0 to maximum. So the amplitude at the nodes is 0, and the amplitude at the antinodes is maximum. So it means unlike a stationary wave where the waves had the same amplitude unlike a progressive wave where the particles had the same amplitude, for a stationary wave, the amplitude varies from 0 at the nodes to maximum at the antinodes. Also, at points between successive adjacent nodes, the vibrations are in phase. What do I mean by that? If we have a node here and this is the next node, at points between these two nodes, particles always vibrate in phase with each other. At points between two adjacent nodes, particles vibrate in phase with each other, but they will vibrate in antiphase with the particles in the next segment or in the next after the second node. So a particle here A is going to vibrate out of phase with the particle B. But if we have particle P and Q here between these two nodes, particle P and Q will always vibrate in phase. They may not have the same amplitude, but each of the particles reaches its maximum at the same time. After all, they don't reach the same maximum, but each of them has its maximum. So they will both reach at their maximum at the same time while vibrating in the same direction. So for a stationary wave, at points between successive or adjacent nodes, the vibrations are in phase. So it means the medium is going to be split up into what we are going to call segments. The particles in a segment are always going to be vibrating in phase. Now a segment is going to be that one between two nodes. So the particles in one segment are going to be vibrating in phase. Then the particles in one segment are out of phase with the particles in the neighboring segment. So like I said, let's say we have three nodes here. So this is going to be one segment and the other one is going to be another segment. So the particles here are all in phase with each other. But if the particles here are vibrating downwards, the particles here are going to be vibrating upwards. So this is a segment and this is a segment. Particles in the two neighboring segments will always vibrate 180 degrees out of phase. That is for a stationary wave. So therefore, particles on either side of a node are 180 degrees out of phase. Particles on either side of a node are always 180 degrees out of phase. Particles on either side, so if this is the node, particles this side are 180 degrees out of phase with particles the other side. But particles between two nodes are always going to be vibrating in phase. But of course, all particles are going to have the same frequency apart from those, except at the nodes. Because at the nodes, after all, particles are permanently at rest. So all particles will have the same frequency except at the nodes. Okay. So now that we have been comparing stationary waves to progressive wave, then we need to give a summary of the differences between a stationary wave and a progressive wave. So this table is summarizing the difference between a stationary wave and a progressive wave. First of all, the stationary waves, they do not transfer energy, yet for a progressive wave, energy is transferred from one point to another. For a stationary wave, we have seen that the amplitude of vibration varies. It is 0 at the nodes and the maximum at the antinodes. For a progressive wave, all particles will always reach the same amplitude. So for a progressive wave, amplitude of vibration is the same at every position along the length of the wave. All particles will reach the same maximum displacement for a progressive wave. Yet for a stationary wave, particles at the nodes are not vibrating, yet particles elsewhere will vibrate with different amplitudes up to a maximum value at the antinodes. Then between adjacent nodes, all points of the wave vibrate in phase. We have seen that between two nodes, particles vibrate in phase. That is, all particles of the string are at their maximum displacement at the same time. There is a phase change of pi only at the nodes. So after the nodes, the phase now changes. Yet for a progressive wave, two neighboring particles along the wave, a particle here and the next particle, two adjacent particles, can never be in phase because they will not always be at the same stage in their motion. So here uh, phase varies continuously along the wave. All neighboring particles or all neighboring points along the wave are out of phase with each other. They reach their maximum displacement at different times. So even though they all reach the same amplitude, they do not reach their amplitude at the same time. Yet here, all particles in the same segment reach their amplitude at the same time. So here, neighboring particles, two adjacent particles, except at the nodes, they are in phase. Here, two adjacent particles can never be in phase. They are always at different stages of their motion, so they reach their maximum displacement at different times, so they can never be in phase. Then here we have the nodes and antinodes which do not move along the wave. For a progressive wave, we saw that the crests propagate from one end to another end. Only certain frequencies can result in stationary waves depending on the length of the string. For example, we have said that in general, Fn is equal to n times F naught, where n is equal to 1, 2, 3, and so on and so forth. So it means certain frequencies are going to be skipped. If F naught is 10, that means F1 is going to be 10, F2 is going to be set 20. It means 21, 22, 23, 24 has been skipped. So only certain frequencies can result in stationary waves depending on the length of the string and the speed of the wave. All frequencies can support progressive waves. That is the difference between stationary waves and progressive waves. All frequencies can support progressive waves, yet for stationary waves, only certain frequencies can form stationary waves. Note: a stationary wave can be explained by using the principle of superposition. A stationary wave formed by waves on a string may be also illustrated in 3 dimensions, as we can see here. In a 3 dimensions, so I have been drawing loops where here, of course, this is what you see if you try to demonstrate a stationary wave in the laboratory. That's what you see, something like that. It appears as if it is 3 dimensions. So at these points here where particles are permanently at rest, from this animation here, you can see that there is a node somewhere there, and then I'm trying to locate a node, another node, and so on and so forth. So a stationary wave formed by waves on a string can also be illustrated in 3 dimensions like this. However, do not forget that at the antinode point of maximum amplitude, particles have maximum amplitude, and the node, that is a point of 0 amplitude. So we shall explain a stationary waves using the principle of superposition later on. So how do we graphically represent a stationary wave? So graphical representation of a stationary wave, I think this is the hardest part of stationary waves. So the set of animated graphs below represent 2 progressive waves of equal amplitude, which means when there is destructive superposition, the resultant is 0. They have the same frequency, they are moving in opposite directions. So we are going to assume that they have the same type, so they have the same speed. When a string is clamped at the right hand end, the effect of the clamp is to change the phase of the reflected wave by pi when it returns. So we are going to consider 2 waves. Let's say the blue wave is the incident wave which is moving, or let's say the blue wave is moving initially from left to right, which is the progressive incident wave. And let's say the red wave is the one which is moving from right to left. These 2 waves are combining at certain points to form the resultant, which is black. Now I want you for a second to just look at the animation when the blue is perfectly getting aligned with the red. For example, in this situation here, when the blue is perfectly aligning with the red, you notice that the amplitude of vibration is bigger. In another scenario, I want you to look at a point where the blue crest is perfectly aligned with the red trough. For example, in this situation here, when the blue is aligned with the trough, the blue crest is aligned with the trough of red, we have zero amplitude. So whenever there is a crest aligning with a trough, we shall have zero amplitude. That is the resultant. And whenever we have a crest of blue aligned with a crest of red, we have maximum amplitude. That's what we are seeing at this point here. So this is what we call a formation of a stationary wave. And I've said here we shall have where particles are permanently at rest. On the resultant wave, this is where we have the nodes. The nodes do not propagate through the wave. They remain in their same positions. And here, where particles vibrate with the maximum amplitude, is where we have the antinodes. So the black line is showing the resultant after the two waves have combined. So that is the graphical representation of a progressive wave. Now this animation is going to help us understand what happens in the next part. So the positions, or there are some positions, the nodes, where the displacement of the resultant is zero throughout the cycle. That is where I have written n. The displacement of the resultant at the antinodes fluctuates from a maximum value when the two progressive waves are in phase to zero when they are out of phase. So you notice that somewhere here it becomes zero at the nodes, and then it increases and to a maximum, then it decreases to zero, and so on and so forth. So that means the amplitude of vibration varies for a stationary wave from zero to maximum back to zero between the two nodes. Yet for progressive waves, for these ones, the red and blue, they are having the same amplitude throughout. So that's why you see for the black line, it is growing. At some point, it becomes horizontal. It grows to maximum, and so on and so forth. Yet the others are just changing direction as the blue crests move from left to right, and the red crests move from right to left. So the displacement of the resultant at the antinodes fluctuates from maximum value when the two progressive waves are in phase to zero when they are out of phase. So that is the graphical representation. So we have to now interpret these two. So to interpret these two now, I'm going to just consider the situation when they are now fixed. So this time I'm going to use the green and the dotted lines to be the incident and the reflected progressive waves. Then I will use the red solid line as the resultant of the two. So we have all along been seeing that whenever a crest is aligned with a trough, we have maximum amplitude. So we have the antinodes at these points here. We have the antinodes at those points. And whenever a trough is aligned with a crest of the two waves, a trough of one wave is aligned with the crest of another wave, we have the nodes as we have seen from the animation above. So we are going to start capturing our graph at t equals to 0 when we are starting with the maximum displacement. We are starting with this position here. A crest is aligned with a trough. What happens after, say, a quarter a cycle? So the red dot is a wave moving from, say, left to right. The blue or green dot is a wave moving from right to left. And then the red solid line is going to represent the resultant wave. So graph A is going to catch the waves at an instant at which they are just in phase. That is the green and the red dotted lines are just in phase. Now we are going to consider the situation what happens after a quarter a cycle. At t equals to 0, they are just in phase. Remember, the green one is moving, say, to the right. The red one is, the red dotted is moving to the right, and the green one is moving to the left. At a quarter cycle, it means a crest of the green crest of the red one has moved a quarter a cycle to the left, and then the green one has also moved a quarter a cycle. Sorry, the red one has moved a quarter of a cycle to the right, and the green one has moved a quarter a cycle to the left. So what has happened? So a quarter cycle to the right and a quarter cycle to the left. So it means those two corresponding crests are going to be half a cycle. They are going to be half a period apart or half a cycle apart. If at t equals to 0, they were we consider these two crests which are perfectly aligned. After a quarter a cycle, the crest of red has moved to the right, a quarter cycle. The crest of the green one has moved to the left, a quarter cycle. So it means the two corresponding points that we consider at t equals to 0, they have therefore moved a half a cycle apart from each other. And they're half a cycle apart from each other. It means if I try to find the phase difference between those two corresponding points, the phase difference is going to be equal to, let me say, 360 degrees into time out of step divided by capital T. So if the time out of step is now half a cycle, so the phase difference is going to be 360 into half a cycle divided by capital T, which gives us 180 degrees. So it means the two particles are now 180 degrees out of phase. And 180 degrees out of phase is called antiphase. So at that point, it means after a quarter cycle, a crest is going to align with a trough. That's why we are seeing a crest aligning with a trough after a quarter a cycle. And this is destructive interference. The resultant is going to be a horizontal line. I don't know that this horizontal line is visible. So the resultant wave is a horizontal line after a quarter a cycle. The resultant wave is a horizontal line, which means at a quarter cycle, we just see a destructive interference, which is going to give us a horizontal line. So superposition gives the curve which has twice the amplitude of either of the progressive graphs, that is at t equals to 0. Then graph B is the situation a quarter of a period cycle later, when the two progressive waves have each moved a quarter of a wavelength in opposite directions. So a quarter to the right and a quarter to the left. This means it is a half apart. Two corresponding points which we have considered at t equals to 0 are now half a cycle apart. And half a cycle apart corresponds to the struct 180 degrees. So it means our crest is now going to align with the trough. That's what we are calling destructive interference or in antiphase. So the movement of one relative to the other is half a wavelength. They're now half a wavelength or half a period. So the waves are exactly out of phase or in antiphase. The resultant obtained by superposition is going to be zero amplitude everywhere. So at that instant, we shall see zero amplitude everywhere. That's why from the previous animation on the previous graph, at some point we're seeing the line to be horizontal. Maybe I can take you back here. Let me first go back. So when you look at the black line, there's an instant where the line becomes almost horizontal, only that I couldn't pause this animation. But you see the black line grows, there's a point where it becomes horizontal along the horizontal line. At that point, that is after now a quarter cycle, that's what we are having. We would see a horizontal line as the resultant, but it doesn't of course last long when other cycles start coming in. So that's what I'm really talking about here. So after a quarter cycle, a crest is going to be aligned with a trough, and in that case, we shall have destructive interference. And for destructive interference, we expect the resultant to be a horizontal line along the x-axis, or we expect the resultant to be just a horizontal line because we have total destruction or destructive interference. I've showed you what happens here. At t equals to a quarter a cycle, it means the wave moving to the left, to the right, a point has moved a quarter of its cycle to the left, to the right. For a point moving to the left, it has also moved a quarter of its cycle to the right. So the 2 points are now going to be a total of a half a cycle apart. So if I try to find the phase difference between them, this will be 360 into the time out of step is a quarter divided by capital T, which gives us 180 degrees, or which is the same as pi radians. So pi radians is antiphase, and in antiphase, a crest is always aligned with the trough. When a crest matches or aligns with the trough, we have what we call total destructive interference or total destructive superposition, which results to zero amplitude. So we would have a horizontal line in that case. Let's now think of a situation where we now look at the wave when t is 3 or when t is equal to half a period. After half a cycle, half a period. So in C, now for C, t is equal to half a period. So it means if we considered the particles initially at t equals to 0, after t equals to half a period, the particle which was moving to the left, to the right, has moved half a period to the right, and the particle which was moving to the left has also moved half of its cycle to the left. So the two particles, therefore, after half a cycle, are going to be a total of a full cycle apart. A full cycle apart is equivalent to one wavelength, or a full period apart is equivalent to one wavelength. So that means the phase difference here is going to be 360 degrees. And 360 degrees is going to be called constructive interference. So again, a crest is going to align with the trough. But because we started with this being upwards, this is going to be a reverse because after one cycle, there is a reverse. So now what arrived as a trough, a crest, will now return as a trough, and so on and so forth. So there will be a reversal of there will be constructive interference, but there will be in the reverse. So graph C, half a period from the start. The waves are again in phase with the maximum displacement for the resultant. That's why you see the peaks are now big as for the resultant wave. So we have maximum displacement. So the process is going to continue. The process continues again after 3 quarters. Destructive comes back where the resultant will be 0. So we have a horizontal line as the resultant. So the process continues through graph D, showing the next out of phase situation with the 0 displacement of the resultant everywhere. And again, finally, after now capital T, after one period of these two waves, so one is going to be a period the other side, a period the other side, so that is again 2 periods apart. So 2 periods apart, it means again a crest is going to align with a trough. So finally we go back to where we started from. So finally the graph E, one period from the first brings the wave into phase again as in A. So this is what happens after one complete cycle of each of these two waves. After one complete cycle of each of these two waves. So we now go back to where we started from, and then the process continues, and so on and so forth. So this is how we interpret these graphs. The graph part here is the hardest, I think, in waves. This is the hardest part. But you can check out the solved past paper questions if you need more clarity for these waves. Until next time, bye bye.